Okay. So what is
Yeah.
simple, what will simplify a lot here the problem is that the diameter is given and the flow rate is given. So first we calculate the velocity by saying V equals Q over A. Once we have V, since the diameter is known, we can calculate Reynolds. Okay. And of course, since D is given, then epsilon over D can be calculated. So here I have two known inputs. Therefore, I don't need to do any assumption. So now, since I have two inputs, which are Reynolds and epsilon over D, I will go to my Moody chart to get F. Let us do it together. Okay, so let us go to Moody chart. What is the value of Reynolds? It's nearly, if I have 1, 2, 3, 4, 5, I have nearly 7 times 10 to the power 5 as Reynolds, and epsilon over D is 0.0017. So let us take these two values and plug them into Moody chart. So this is the Moody chart. Okay, so first in green, you can see the curve of epsilon. So to remind you, this axis is for epsilon over d. Okay, the green curve, it's not the green curve is not in the Moody chart. I draw it for you. So how you find it? It's very simple. And you have, this is the curve for 0.001. This is the curve for 0.002. So nearly you will take an approximation. No, it will be more close to 0.002. So you put it in, you draw it, you draw the approximate curve for epsilon over d corresponding to 0.0017. And you know that Reynolds is 7 times 10 to the power 5. So you take it up, and the intersection, this is the intersection point. Once you find the intersection point, you can read the corresponding value of the friction factor. So here, since I know two of my inputs, I don't need to do any assumption. And going to my Moody chart, I can find the friction factor. Okay? Now, once I find my friction factor, I can replace it in my energy equation back. So I will go back now to my energy equation, and F is now known. The friction coefficient is equal to 0.0227. So if I replace back into my energy equation, the only unknown will be what now? Will be the head of pump. Okay, so by replacing F by its value, I can calculate the pump head. And once I know the pump head, how to calculate the power? If you remember last time, we said that the useful power, P useful, of a pump, okay, is equal to gamma times Q times H, okay, because it's Q, if you want to remember, it's Q times a pressure, and the pressure here is rho GH, it's the hydrostatic pressure, okay, so the useful power is Q times rho times G times HP, and if you want, this pressure is not, if you want, it's not physically a pressure, but it's equivalent in units, okay? Because rho G HP, we call it turbine pump head, okay? So the unit of HP is in meters, so it's equivalent in units to, when I multiply it by rho G, it will be equivalent to the unit of a pressure, okay? And you know that the power unit is equivalent to the unit of the volumetric flow rate times the unit of the pressure. So to know the useful power of my pump, it is equivalent to Q times rho times G times HP. Okay, so don't confuse this term rho GH. It's true that it has the same form of the hydrostatic pressure, but it's not a pressure physically. It's the pump. It's due to the pressure created by the pump. Yani it's the energy of the pump. Okay. So this is the useful power of the pump. And now, since they need the total power and the efficiency is given, I can say that the efficiency is equal to the useful power, P useful, okay, over P input. And now, since I know P useful and I know the efficiency, which is 0.75, I can say that the power that should be delivered to my pump is gamma QHP, H pump, over the efficiency. Okay? And in this way, I calculated what is the power needed to drive my pump. Any question on this
Okay.
problem? Yes?
Yes, please.
أول شيء الإيكويشن اللي نعرفها P equal rho G QH P over
Yes, last time I introduced
over
it to you. Last
efficiency.
time. I don't know if you attended last session. So you have that power as unit is what? Is in watt. Okay? And you know, if you have taken dynamic course, power can be calculated as force times watt times velocity. And the force as a unit is equivalent to pressure times area. Okay? So the unit of power is equivalent to the unit of pressure times area times velocity. And you can replace AV by what? By Q. So the power as unit is equivalent to Q times the volumetric flow rate AV times a term having the same unit of pressure. Okay? For a pump, what is the term that will have the same unit of pressure? It's the pressure head, if you want to say. The head of the turbine HP is defined in a way that if you multiply rho G by H, you will get the if you want the equivalent pressure energy of the pump. Here you have energy can be in different forms. It can be in form of pressure. It can be in form of motion, kinetic energy. Okay, it can be in form of hydrostatic, and all of them will have the same unit. Okay, so if you do when you do for pressure, the pressure for equivalent equation for the pump will be rho GH pump. The hydrostatic pressure is rho GH, the actual H, while the equivalent term for a pump is rho G head of the pump. Okay, this is why when you want to compute the power of the pump, you will do rho G, which is gamma, times H, which will give you a term that has a unit equivalent to pressure, and then you multiply by the volumetric flow rate to get the power of the pump, useful power. And since you need the total power, you divide by the efficiency.
Okay, different. بس one more question. فينا نرجع الصورة اللي فوق please.
Yes. Yes.
هون إذا بدنا ناخد الماينر لوسز
Yes.
هيكون عندنا بس one inlet one outlet أو بدنا ناخد كمان تقول البامب.
No, ما البامب انتبه، البامب كلها سوا مثل closed box، يعني هي HP
بس بتفوت فيها بتظهر.
ال HP هي overall، يعني in overall. اوكي ما بتفوت in details شو بيصير بقلب البامب. اوكي
طيب باك بليز فوق على اليمين محل ما فايتي فوق إذا بدنا نعتبرها هيدي شو بنعتبر الكونكشن؟
هلا here look here إذا في angle بدهم يعطوك table مع إنه representing إنه إذا في angle يعني هيدي بدها table خصوصي لها، بدها figure خصوصي لها. اوكي so they should give you or they tell you take the coefficient plus here equal to this, or they should provide you with a table having one of the option an exit like this. Okay
يعني دغري فينا نعرفها من التيبل صح؟
اكيد اذا موجوده بالتيبل يس. يعني انت في كثير تيبلز وفي كثير اكسبيرمنتس مفروض انه هن بالفحص اذا عطوك هيدا الشيء وبدهم اياك تحسب الماينر لوسز they should give you the corresponding figure.
Okay.
Any other question on this problem? Okay, so let us continue with the problem. Another problem. A tank contains 1 meter cube of water at 20 degrees and has a drawn capillary outlet tube at the bottom as shown in the figure. The outlet tube, find the outlet volume flux Q in meter cube per hour at this instant. Okay, so here Q is not known in this problem, and if Q is not known, so since D is given, so V is unknown. Okay, so now as usual we start by the typical method. We start to write the energy equation from position 1 to position 2, starting from here to here. Okay, now since whenever you have a large reservoir, you can say that approximately V is neglected at this level compared to the second one. So I can say that here P1 is 0 since it's exposed to the atmosphere. V1 is 0. And for the elevation, okay, I have here the initial elevation is, if you want, I should take a reference. if I take my reference here, for example, or if this is 0, let's say z equals 0, if this corresponds to z equals 0, then I have to take that z1 is equal to 1 plus this length, which is 0.08 meters. If you want, sometimes you can say since it's very small, I can neglect it. يعني بس إنه if you take it into consideration, it will not affect a lot your result. Okay, so you can say that z1 is equal to.
دكتور هي 0.8.
نعم.
0.8.
Yes, sorry, 0. Yes, exactly. It's divided by 100. So 0.8. So yes, you should not neglect it then. Okay. So you have here then z equal here to 1.8. So it's 1.8 meters. Okay. And concerning 2, at level 2, you are exiting at the atmospherical level. So P2 gauge is 0. And for V2 is unknown. Okay, because Q is not given here. So the first step I will do is to write the energy equation. And also here they said neglect minor loss. If they don't say neglect minor losses, I should take losses at which level? You have here. Okay, you have losses here, and here also you have losses, because when you have discharge to environment also this will cause losses. So you should compute losses here and here. And you can see
كيف نطلعه؟
نعم
تحت كيف نطلعه؟ نحن نعرف بس انه اذا عندنا variation بالاريا.
بيعطونا كي exit انه if I have an exit to open atmosphere, what are the corresponding losses.
كمان بالتيبل.
Yeah. Okay. So now what I will do, I will write the energy equation. Okay. And I will start to simplify terms. So here when I write and I simplify pressure and V1 is 0 and Z2 is 0, I end up with the following relation, that the losses, which are equal here only to major losses since we neglected minor losses, is equal to FL over D V square over 2G equals to delta Z between 0.1 and 2, and this term V2 is not, yani V2 is unknown, so I found a relation between friction factor and V2. Okay, so delta Z is known, so the only unknown here are F and V. Okay, so when by writing the energy equation, I got a relation between F and V, but since both are unknown, yes.
When they took the velocity V.
Yes.
to be يعني قبل كنا نشيل
V1 equal to V2 بلاي.
هون أخذوه بذاته. Okay.
Yes. V is equal to V2 لأنه أنت أصلاً هيدي الميجر losses وين بتصير بس بأي part؟
البايب.
بالبايب from here to here. Okay. So then you have along this whole path. Okay. You have the same velocity since you have the same cross-sectional area. So V2 is equal to the average velocity here. This is why they expressed both as V. Okay? Because
ليش بس بالبايب؟
نعم.
مش فوق كمان عم تمشي velocity غير اللي بالبايب؟
لا بلا بس فوق velocity قد nearly zero. Why? Because you have a very large area compared to this one. So you are neglecting.
بكل ريزرفوار
فوق you neglect velocity فوق. Okay.
كمان هيك ما اخذنا تو velocities طلعنا الافريج بيناتهم.
مظبوط. اصلا انتبه ما بتاخذ تو velocity وبتطلع الافريج بيناتهم. اذا عندك two different velocities you treat
بشتغل وحده من فوق وحده من تحت.
you treat each part separately. يعني بتقسم الميجر losses بهال part function of the average in this part والميجر losses ب part 2 function of V2. but how you can correlate both في relation بين ال velocities اللي هي انه through the equal volumetric flow rate. يعني لو عندك اذا بدك هون الكروس سكشن مش كثير كبيره فيك تكتب انه في relation V1A1 equals to V2A2. ساعتها if we want to calculate in this part in this case ساعتها بناخذ major losses in first part و major losses in second part separately, but the correlation between them انه في relation between their velocity. يعني if I know V1 I can get V2. اوكي بس ساعتها اجباري. نعم
حنحل هيك شيء؟
يس بنحل هيك شيء ما في بروبلم. يس بركي next time بحضر لكم هيك شيء.
هون ليش ما قلنا انه V1A1 equal A2 V2؟
لانه هون A1 كثير كبيره و V1 كثير صغيره، يعني in a way انه V1 قد ما A كبيره V1 is nearly zero. عرفت كيف؟ لانه V1 is nearly zero
okay.
يعني losses nearly zero because loss is proportional to V square. يعني اذا عندك very high very low velocity they will be neglected. Okay.
اوكي تمام.
Okay. So now we got a relation.
فينا نطلع diameter فوق.
نعم.
فينا نطلع diameter فوق.
فينا نطلع هلا هون اذا بدكم هن يمكن مش معروف اذا فوق it's a rectangular shape او circular shape. اوكي. Anyway اذا كان circular shape yes فيك تطلع الدايمتر وفيك تعمل corresponding calculation. اوكي. فيك ساعتها to verify بس in general يعني حتطلع كثير كبيره compared يعني هون عندك 4 سنتيمتر، هونيك عندك اكيد شيء اكبر بكثير لانه عندك الكروس سكشنال اريا 1 متر سكوير، فعمول باي دي سكوير over 4 you get d will be much larger than 4 centimeters. You can try to do comparison حتبين انه velocity will be negligible compared to this.
بس انا قصدي امتى we assume this ما بنشتغل باللي فوق، وامتى انه بنجرب نحلها ونعمل relation.
يعني مثلا اذا مثلا اعطوك هيك، اذا اعطوك تيوب قالوا لك 6 سنتيمتر وتيوب ثاني مثلا 4 سنتيمتر، يعني اكيد ما you cannot neglect ساعتها، يعني لانه حيصير صحيح انه الفيلوسيتي اصغر بس انه مش بكثير. اوكي. يعني بهيدا الكيس مثلا if you have the diameters not يعني diameters are not very far from each other يعني they are nearly close، ساعتها اجباري تقسم على 2 parts. يعني هون you can verify you can calculate d and compare the two d's. إذا كان كتير في فرق you can say إنه I will neglect. If not you should divide into 2 parts as here. okay. جربوا إذا بدكم قد ايه بتطلع دي تقريبا، يعني أنتوا عندكم باي دي سكوير over 4 equal 1، يعني عندي دي سكوير equal to 4 over pi. 4 over pi أكبر من 1، يعني دي حتطلع أكبر من 1، دي أكبر من 1 متر. أوكي. بينما دي 1 بينما دي 2 بالتحت 4 سنتيمتر يعني divided by 100 يعني 0.04. فشفتوا الريشيو شو كبير، وحتى انتوا الريشيو proportional لدي سكوير، يعني فيكم تقولوا انه V1 over V2 هي equal ل D2 square D2 square over D1 square D2 square over D1 square اللي هي حتطلع هون equal ل D2 over D1 هي 0.04 وعملوها square تطلع 0.016، يعني its velocity is less than 1.6% فوق من تحت. This is why we can neglect here. Okay.
Okay.
So now if we continue from this relation we got an equation relating V and F. Okay. هلا here if you want to calculate Reynolds number, Reynolds will be function of V. Reynolds is function of V. مظبوط. يعني if I write Reynolds فإذا قلنا على طول third step I write second step is to use Q، بس Q already استعملناه. Q equal A times V وأنا ما بعرف Q أصلا هون. Q is not known. يعني this is why I will not benefit from writing Q equals A here. Okay. بس بستفيد منها إذا عندي إنه if I have two velocities, I can say that V1A1 equals V2A2. That's it. Here for Reynolds is rho V d over mu. V is not known. يعني Reynolds function of V unknown. Okay. Epsilon over D. نعم.
We have to guess for V.
Yeah, we have to guess for F. Here we will guess for section. Okay.
To find
always يعني هون عنا the diameter is given, so here this will simplify the assumption for F. يعني نحن عنا epsilon over D بنعرفها. When you know epsilon over D, always start by the assumption that correspond to the flat curve. يعني أنا هون what is epsilon over D? It's 0.0000035 375. I can go to Moody chart. Let me see if it's here. Okay, أنا ما حطيت لكم إياه هون بس let us do it together. So 0.000375
هو لما اصلا
يعني تقريبا هون تلاقوا تقريبا close to 0.000375 close to 0.0004. فأحسن شيء يعني أنا إذا برسم الكيرف الجرين كيرف الفلات كيرف حتكون on this level. فإذا بتاخذوا الفلات كيرف على الآخر يعني هي الفلات كيرف in green أكيد. أوكي. إذا بكملها على الآخر تشوف what is the corresponding value of f شو بيطلع لي f 0.015. So the best guess to start with here is f equal to 0.015 since it corresponds to the flat part of epsilon over d in the problem. يعني هون epsilon over d هي 0.000375 which is very close to 0.0004. يعني إذا برسم تقريبا الكيرف تبعها بتطلع الفلات بارت هون الفلات بارت. This is the flat part أول شيء أول part بعدين بتصير curve. Okay, so for the flat part what is the corresponding value of f? It's 0.015. So I will go for it. Okay, I will start by this guess and now if you start by this guess you can find velocity. Once you can لأنه you replace in the energy equation مظبوط. So if I guess f I can find what here? I can find velocity. And once I have velocity I can find Reynolds. Okay. هلا صار معي two inputs. صار معي Reynolds و epsilon over d which is known already. But now I go to Moody chart. I find the new f. The new f I find بتطلع 0.0158 very close. Okay. هلا فيني إذا بدكم هون I do the difference. تطلع مفروض أقل من 10%. So I can stop إذا أنا الكرايتيريا let's say is 10%. Okay. فهي بعتقد تطلع قريبة من 5%. So it's fine. It's okay for me. So I can stop here and I say I reached convergence. So this is the corresponding value of f. I replace into v, I get v. Okay. And now since I have v and I have the diameter, I can calculate the flow rate. Okay. That's it. So here
هو لما جاب ابسلون على دي
نعم
اي دي اصلا
اوكي دي given اكيد ال 4 centimeters below 4 centimeters because انت وين
اوكي خلص داري
انت هون وين عم تعمل اللosses in this section اوكي لانه قلنا فوق we will neglect because v is nearly zero. We are working on the losses in this section corresponding to a diameter of 4 centimeters.
اوكي ديل تمام.
Okay. Any other question on this problem? Okay. So as you can see يعني if you do some practice حيصيروا يعيدوا بعضهم ال problems يعني. It's always the same method. Just I should know إنه in each case with what to do depending on the variables I have. So another problem.
دكتور هيك هن كلهم types of problems.
ايه هلا هعملكم بعد هيدا البروبلم فيه two velocities مثلا هيك هيدا اصعب شيء معقول يجي وغير هيك هول هن التايبس اوف بروبلمز يس
انه ما في عندنا هول اللي شرحهم دكتور نديم اخر 40 minutes تقريبا.
شو شرح دكتور ما بعد ما خلصنا بروبلمز بعد في كم واحد عم نعمله يعني انا حاعمل بعد كم نعم
شيء عن الهاد تاع التيربولنت ما تيربولنت هيك
I will do corresponding problems on them.
Okay.
So you have now in this system we have you have several fittings. Okay, so the system in the figure consists of 1,200 meters of 5 centimeters cast iron pipe. So as usual the type of the pipe بيعطينا الابسلون. Okay. So هون لأنه SI unit حجيب الابسلون in millimeter وحولها لمتر. I have 245 degrees and 490 degrees flanged long radius elbows. So I should go to a table to look at flanged long radius elbows for two angles, 45 and 90. I have a fully opened flanged globe valve and a sharp exit into a reservoir. If the elevation at point 1 is 400 meters, what gauge pressure is required at point 1 to deliver a volumetric flow rate of 0.005 meter cube per second of water at 20 degrees into the reservoir? So here also, first step, here they didn't say neglect minor losses. Okay, and of course it's clear that I have a lot of sources for minor losses, so I should take them into account. Okay, plus أعطوني إنه the minor loss coefficient for a fully open flanged globe valve اللي هي هون أعطوني إياها. يعني يمكن ما رح يعطوني table فأعطوني الفاليو تبعها. Okay, so for this one it's okay for me. I still need to find for my 40 degrees and the 240 degrees. And I have, they said that I have 490 degrees. حتى لو ما قالوا لكم هن the number, you can look at the figure. So I have 240 degrees, and for 90 I have 1 and 2, and here's 3, and here 4. So 245 and 490. Okay. Now to find the corresponding K, I will go to search for in the figure. If you go to the figure here, first from the table of roughness, من cast iron, I get that epsilon is 0.26 in millimeters. And pay attention, since you are working in SI, D is in meter, so you should convert, you should do times 10 to the power minus 3. Okay? And now, if I go to my table of fittings, I can see that for a long radius of 90 degrees flanged elbow, it's 0.2 as coefficient of loss. And for an angle of 45 degrees, it's also 0.2. So for both, K will be equal to 0.2.
أنا sharp exit أهم شيء.
وأنا sharp exit فبدنا نطلع بهيدا الفيجر. For the sharp exit, I have K equal 1. But then I found all my coefficients. And if I look here, since I have one diameter from the beginning to the end, I can say that sum of K, I can sum all K's in one term and take V square, the term of V square as outside. So sum of K, I have 2K of 45 degrees plus 4K of 90 degrees. And don't forget the K of exit. And also here I have the K of the open valve. So this is the
ليش
whole.
ما أخذنا 2 open valves؟
نعم.
إنه محل ما فايته ومحل ما ظهره.
في عندنا واحدة.
هي بناخدها كلها كوحدة، مش إنه محل فايته ومحل ظهره.
كلها كوحدة. Yes. Okay. So.
5 centimeters هي diameter.
نعم.
5 centimeters هي diameter.
8 centimeter. وين في 5 centimeters. Yes. He diameter, yes. Okay, so the diameter is given here. So first, as we said, we find epsilon. We have the diameter. We get epsilon over D. Then, since we have also, they are giving us the flow rate. Okay, the flow rate is given. From the flow rate, since we know the cross-sectional area, which is pi over 4d squared, we can calculate the velocity. And since the velocity is known, we can get Reynolds number. And here also it's a simple case because we know Reynolds and we know epsilon over D. Hence, we should only go one time to the Moody chart. By putting these two inputs, we can get from Moody chart what is the corresponding value of the friction coefficient. And now, after finding the K for all components, as we said, we are ready to write the energy equation. So when we write the energy equation, as we said, we have that P2 and V2 are 0, because if you go back to the figure, okay, we are exiting to a very large reservoir exposed to atmosphere. So pressure is 0 and velocity is 0, okay? And you have that V1, which is the inlet velocity, is equal to the average velocity in the duct, since we have a constant volumetric flow rate and constant cross-sectional area. So here V1 is equal to V, okay? So when I write my energy equation, I have that P1 over rho G plus V1 square over 2G plus Z1 equal to 0 plus 0, which correspond to P20, V20. Now for the losses, I should consider major and minor. This is major losses, and this is summation of minor losses. Okay, so now I have everything in my problem. The only unknown will be P1. Okay, because I have found already, we have found together what is summation of K. Okay, and you know that to compute the losses, what do we do? We multiply summation of K by what? So losses is, so minor losses, sum of H minor is equal to summation of K
times V squared
times
over
V
2G.
square over 2G. Okay, and here what is V squared? It's V1. Okay, why? Because as we said, V1 is equal to the average velocity V, since the value is not changing, the velocity is not changing over the duct, since we have a constant cross-sectional area. Okay, so and also HF is computed as F times L over D, where F is the friction factor we found from Moody chart. L is the total length of the duct it is given, and D is the corresponding diameter of the pipe. Okay, so also we multiply by V average, which is here equal to V1, V square over 2G. So if you take V square over 2G into factor, okay, V was found to be 2.55. You can express P1 function of all of these terms which are known, and the only unknown will be P1 you can get. Okay, and this was the question: what is the pressure at level 1 to have the corresponding flow? So we are done also with this example. Okay, so next time hopefully we can continue. We still need one session to finish. Okay, and if you have any questions, as usual, you can send me by WhatsApp, or we can do office hours when you want to explain for you. Okay,
Okay, thank you, doctor.
welcome.
Thank you.
So, doctor, can you
Yeah.
upload the document هيدا على Blackboard?
Yes, I will. I will today. I will upload it.
Okay, thank you.
Okay. Bye.